The central problem of telecommunications is a clash of formats. The physical world produces continuous, analog signals, but networks require discrete, digital data to function. To bridge that gap and move an analog reality across a hostile, noisy physical channel, we force the data through a highly specific, universally applied sequence of mathematical operations. This handwritten block diagram shows the foundational architecture of all modern digital systems. Following the path from the source input on the left, the signal is digitized, compressed by the source encoder, mathematically armored by the channel encoder, modulated into a physical wave, and sent through the physical channel before the receiver reverses the process. Every operation in this pipeline serves two primary, often competing goals: maximizing efficiency by compressing the data, and maximizing reliability by strategically injecting redundancy back into the stream. In 1948, Claude Shannon established the fundamental mathematical ceiling for both of these operations, proving exactly how much data a given channel can hold before errors become inevitable. Because of these hard limits, this pipeline is a continuous optimization problem, balancing available bandwidth against transmission power and the acceptable bit error rate. The pipeline begins by converting a continuous analog wave into a finite digital bit stream. The standard method for this is pulse code modulation, or PCM. Looking at this PCM encoder block diagram and the ideal sampling waveforms below it, we see the first critical phase, taking discrete samples of the continuous wave at specific time intervals. This chart defines the boundary of sampling. The Nyquist criteria mandates our sampling frequency must be twice the signal's maximum frequency. Failing this threshold causes high frequencies to bleed together, creating aliasing. Once overlapped, the original signal is permanently destroyed. If the sample rate is sufficient, PCM moves to the second phase, quantization. The continuous amplitude of each sample is snapped to the nearest predetermined discrete level, determined by 2 to the power of n, where n is the number of bits. This calculation dictates the system's bit rate, which is the number of bits per sample multiplied by the sampling frequency. This quantization graph maps out the step sizes and the inevitable quantization error that occurs when rounding off the true analog value. Increasing the number of discrete levels reduces this error, but simultaneously drives up the bitrate and demands significantly more bandwidth. To bypass this bandwidth cost, engineers deploy delta modulation. As shown in this step size graph, it transmits only the change in slope rather than absolute amplitude, reducing the bitrate. However, it risks slope overload noise if the original signal spikes too rapidly. Discretization forces a trade-off. We must abandon perfect analog fidelity to produce a digital file size our network can physically carry. Once the signal is digitized, the system executes an apparent paradox. It spends immense computational effort compressing the data, only to intentionally inflate it moments later. The compression phase is source coding. Driven by Shannon's concept of information entropy, the objective is to strip away every trace of statistical redundancy from the file. This probability tree illustrates one of the most efficient algorithms for this task, Huffman coding. By organizing messages in descending order of probability, the system assigns the shortest binary codes to the most frequent symbols. But a perfectly compressed zero-redundancy bitstream is highly vulnerable. Without any extra context, a single bit flipped by static in the physical channel will corrupt the entire message. To solve this, we apply channel coding. We intentionally inject structured mathematical redundancy into the sequence using matrices, giving the receiver a way to detect and correct damage. This block diagram and matrix equation detail linear block coding. A raw message vector is multiplied by a generator matrix to produce an expanded, fortified code word. This generator matrix is built in a systematic form, structurally isolating the original message bits from the newly generated parity bits, making the math reversible on the other side. Looking at this receiver block diagram, we see that inverse process. The incoming bit sequence is multiplied by a transposed parity check matrix to calculate a value called a syndrome. This syndrome error table decodes the damage. If the syndrome is 0, the data arrived intact. If it is non-zero, this exact table maps that specific mathematical remainder directly to the bit that flipped, letting the system correct the error. The paradox resolves into a division of labor. The system strips statistical redundancy to maximize transmission efficiency, but mandates structural redundancy to guarantee the data's survival. Even protected and compressed, binary logic is still abstract. To travel across a copper wire or through the atmosphere, these numbers must be converted into physical energy. This waveform chart demonstrates line coding, the mechanism for converting binary data into electrical baseband pulses. Bits are mapped to varying voltage patterns, such as unipolar or Manchester, depending on the physical limitations of the cable. Because baseband pulses degrade quickly over distance, wireless transmission requires digital modulation to shift these pulses onto a high-frequency carrier wave. We map this conversion using a constellation diagram. By plotting digital symbols onto a Cartesian coordinate system, we define exactly how to alter the phase and amplitude of the carrier wave to represent different bit combinations. Looking at this constellation diagram for 4PSK, we can see the logic. It takes combinations of 2 bits and maps each specific pair to one of 4 unique phase angles on the circle. Examining the signal margins on this page shows how the physical distance between points dictates noise immunity. If constellation points are placed far apart, a burst of static is less likely to push a received signal into the territory of the wrong bit pair. But widening the distance between these points requires either increasing transmission power or consuming a wider block of the frequency spectrum. Digital modulation acts as the ultimate physical anchor of the system. It is where mathematical algorithms must respect the thermodynamic constraints of the universe. Returning to this foundational block diagram, we see these individual components operating together as a single mathematical engine. It is a continuous, unbroken chain of translation. We discretize the analog world at the Nyquist limit, compress it to Shannon's entropy floor, protect it with parity matrices, and geometrically map it onto a radio wave. But the architecture must solve one final challenge. A physical channel, whether a fiber optic cable or a cellular frequency, is almost never dedicated to a single user. These block diagrams outline basic multiplexing. Time division multiplexing interleaves multiple users by assigning each a dedicated microsecond time slot, while frequency division multiplexing carves the channel into narrow, distinct frequency bands. For more dynamic environments, engineers use spread spectrum techniques. This shift register diagram details the generation of a unique mathematical signature called a pseudo-random noise, or PN sequence. By multiplying a user's data with their specific high-speed PN sequence, the signal's bandwidth is intentionally scattered. To other receivers, it appears as low-level background noise, but the intended target can extract it, yielding a connection that is naturally secure and resistant to jamming. The ratio of that spread bandwidth to the original data bandwidth determines the processing gain, a precise measurement of the noise immunity the system has mathematically engineered. From the microphone to the radiating antenna, a digital communication system is an optimized engine built to protect human information from physical decay. Ultimately, telecommunications engineering is the practice of navigating the unavoidable friction between bandwidth, transmission power, and redundancy.